Hi again. So last video we ended up with a script that will give us area information in real time while we're sketching a plan. So we can now very quickly start to analyze area information of a plan while we sketch. However, at the moment, our script is only working for one of the levels. It's only working if everything is on the same plane. So if I were to copy this, it stops working. So what we're going to do now is we're going to add something in the script that will let us separate layers into branches. And then I can take this, copy it onto the first floor, move it to the correct height, and begin to read this properly. Let's just open our script. And the problem is, everything that's being taken from layers called wall lines and division lines is flattened, and it's all meant to be processed together. So we have to add something in between here, which sorts all of these curves into their correct levels. Now, one way would be to divide everything into layers that say wall lines first floor or wall line second floor and so on, and have lots of different inputs for each layer. But an easier way of doing this is to just take all of these curves, read some information about their height. In this case, we're going to do that by just reading the z value from the start point. And once we have that, we can see that there are inputs at two heights, at 6 meters and 0 meters. So what we can do is create a set. A set takes a range of values and turns them into a list of unique values. So it's only going to show a 6 and a 0. So once we do that, we sort those. So we'll get 0, 6, and they're all going to be in order. Graph them, so it'll create a branch for each height, and then try to find for each branch all of the z values that are equal to this height. And if we then take that and use that to eliminate from each branch all of the values that are not at the height specified for that branch, and there it is. We've divided everything into two branches, and each branch has all the curves that belong only to that height. And this is a really useful way of doing it, because I don't need to be very neat about the way that I draw. For example, I can just take this, copy it at any height that I want, even if it's not in the correct layers that I specified, just to make it easier to draw. I could do this. Now we've got 1, 2, 3, 4, 5, 6, 7 levels. And all of those levels are automatically given their own branch and at their own height. So here I can read all of the heights. Well, it's better to do it here. From 0 up to 50. So again, we're trying to do things in a way that makes it as easy as possible to draw. So then that can just be connected to here. And where else? Here. And once we check what's happening, now each of these levels is being calculated correctly because they're all on a separate branch according to their height. Now, the problem is that when you've got multiple levels and they're all getting displayed at the same time, it becomes pretty much impossible to use this as a sketching tool. So we need to find a way to control what level is being shown so we won't be distracted by any other information in this projection. Let's just call this now. Where that's going to happen is going to be right before we display the information. So if, say, we've got 7 levels and 7 branches, we're going to want to control which branch is being shown. And we're going to do that by, let's first bring the information forward here. So we've got our surfaces, and we've got our points on the surfaces where the points are displayed, where the areas are displayed. And we're going to work with these. First, we're going to simplify them because the branch names have gotten pretty complex. By simplifying them, they get much shorter. And these two should match in data structures, and they do. Now, at the moment, there's a branch for every single surface. So we want to shift paths. And so there's only one branch for each level, like so. Now there's only 7 branches, and everything that's contained in them is in that same branch. Now it should be pretty simple to just specify with the slider a branch name. So if I want branch 0, I should be able to select 0. Branch 1, I should be able to select 1. And in order to turn this into a branch name, all you have to do is put it into the correct format. So you've added brackets to the beginning and the end of this, and you just add them in order so that the number is in the middle, and you should be able to extract a tree branch. So this is the branch, this is the data tree, and that retrieves just the information from that branch. Do that for both of these. and just connect those. Just hide everything back here. And you can see that only the information for the selected level is shown. And now this should be working properly in plan as well. Now there is one problem that you'll find, which is kind of a deal breaker at the moment, which is if I delete all of this information, then it stops working. Why? Because if I only have one level, then when I try to shift paths to eliminate the smallest branch, then it just eliminates everything. Because there are no two branches for levels for it to shift to. And to get around this, we're going to have to do a sort of complex trick here, but it's not too difficult. The first thing we want to do is to test for a null value. So if this is a null, this is going to return a true. Now what happens? If this is true, then I don't want to use whatever's here. I want to use whatever's here. And I can do that simply by taking this structure, flattening it to get just the list of items that I would get if it had selected this single branch. And if this is true, if this item is null, I want to keep this information. Now when I do that, and then I merge those two results, it'll either have this information if this fails, or just this information if it succeeds, because then if this is working, then this will be false and this will be eliminated. So there, that's working. Let's just copy this over to this side as well. So we have to do the same thing for this one. And change this. So let's try it. If I duplicate this to another level. No, I think that should have been done there. Okay, yeah. It was a misconnection there. Now it works. So there's two levels, and I can change branches as I find it convenient. And if I remove one of the levels, then it's still working, because then it's caught that error. Now the points are a bit annoying. We might want to hide those. And it's always nice, again, to have your parameters around the same place. And we can label them. Call this level to display. And so you just keep track of what level you're sketching on and make sure that this matches it. And so now you won't have a problem sketching on the correct level. Hi. So in the last video, we learned how to make our script distinguish between two different levels. So it can display, or several different levels, so it can display only the level that you're drawing in with a simple slider. And it's also returning areas in real time as we sketch. Now, we're going to make it even more useful. And we're going to make it be sensitive to what type of program is in each of these areas. And we're going to make it as simple as writing text in the correct level at the correct height. So if I were to write text, and I just write the name of the program, so I wanted to be able to calculate how much area there is in each of these types of program throughout the entire building. So I wanted to pick out all the terrace areas in all of the levels and add them all up and organize them so that we can export them as an Excel sheet, and we can check in real time how much cafeteria area there is, how much exhibition area there is, how much terrace area, and so on. So we're starting with very basic text inputs. Now the way that we're going to bring these text inputs into Grasshopper is using a plugin called Human. And you can download this from foodforrhino.com. And it's a really, really useful plugin to deal with layers and blocks. And one of the things that it allows is a text input. So it can reference a text object. Now, in order to do this, you're going to need two components. First, you have to bring in the actual objects from a layer. Now, this works a bit similar to Pipeline, but it's a bit more powerful because you can specify more types of objects. So first, you need to input the layer name. They're always going to be called text. And the object type. And you can see that it gives you lots of different objects. You can even bring lights into lights as well as blocks. And it's really worth your while to play around with this plugin because it can do amazing things. So we'll just specify text as the type. Then that comes into the text object component, which reads several different pieces of information from the object, including its location and the actual text. So all of the pieces of text that I just wrote are now input, as well as their locations. Now, because we're going to possibly have several instances of the same program name, we might have several terraces and so on, we want to take the text. First, we want to order the text so that it's in alphabetical order. That's going to make it a bit neater when we have lots of different types of program in a Excel sheet in the end. And then we're going to create a set from this. So only unique values. And we're going to graft it. This is similar to what we did when we sorted up all of the curves into their own unique levels. So we're going to sort all of these text objects and locations into a set of unique programs. Now we'll just use the member index component to find each of these members in the list of text inputs. So that'll tell us which indices correspond to this name. And that's going to let us extract those indices from the set of locations. And so now each of these unique sets has the set of points that correspond to it. Now these are planes, so what we want to do is just extract the origin point of the plane, which is the reference point for the text. Now once we have this, what we want to do is find out which of the planes the surfaces that we've already defined with the previous exercises are touching any one of these points. So we're going to graft these points, and for each of these points, we're going to test if it's touching a surface. Now our surfaces were over here before we split them up into branches for easier display. Now we've got a decision to make here, because we don't only want to take into account one level for this tallying exercise. We want to have all levels, but we're going to also want to display information about these different programs on only one level. So what we're going to do is, because we want to switch back and forth between using only one branch and using all of the branches, we're just going to include another toggle for the user here, where if it's false, I want to eliminate this, and if it's true, I want to eliminate this. So we can flatten this at this point, and at the moment it's false, so it's remove this one. And in order for it to keep this, we'll just do a NOT gate. And do the same thing for here. And then just merge the two. So depending on whether you've clicked true or false here, it's going to keep everything or just the level that you're working on. So at the moment, it's only keeping the ground floor. because that's the level that's specified here. So that's what we want to do, just for the moment. So we can just move this switch here. We can say program per level. Yes or no. Okay. So we have the option of taking everything into account or just current level. And then that saves us from other difficulties. So now we're ready to test whether any of these surfaces is touching any of the program points. Just go back to working here for a second. Now we can do this by simply testing the distance of any of these points to any of these surfaces. Now the distance is what's going to tell us if it's touching something or not. So because we don't want to test if it's 0 exactly or not, we're going to say if it's less than 0.01. And then this is just because Grasshoppers are a little bit fussy about how it handles tolerances. And so this will avoid errors down the road. So we can then just eliminate everything that's not touching any one of these points. And so you'll have the corresponding list of surfaces for each one of these points. Now we don't just want the surfaces, we also want the areas. So we'll read off all the areas that correspond to these, and what we can then do is add these together. Let's just test what happens when we compare this with our initial set of programs. There it is. Now this should correspond exactly with what we see here. So we see outdoor exhibition, 520. Oops, sorry. Terrace, 640. Foyer, 197. And so everything seems to be checking out. What happens if I change both of these to foyer? You can see that we've got two branches corresponding to the foyer branch, and they haven't been split up before they were added. So we know that we have to shift the branches at some point here before we take the areas. It would help out a lot if we simplify this. And see, now it's got 2 items in the 1 branch, which corresponds to foyer. And so now, once I did this, that matches up. And so what's happening is that now it's adding both of these areas together effectively. Now this is the basis for building up a program spreadsheet. And you can just be checking this as you're drawing. And so, for example, now we can say that this is exhibition area. We'll just call it exhibition. Go back to calling this terrace. Just as it was. And then let's just look at the perspective. We go to first floor. And switch to our first floor view. And work on that for a bit. And include up here just move our text boxes up there and say that this here is a terrace. We can also hide the ground floor to make this a bit easier to read. Make sure all of your text is in the correct position, in the correct layers. So now I call this terrace, call this exhibition, and now we can check if it's adding up areas in all of the building and not just one level. So now I've clicked the switch to make it calculate program in all levels. And you can see that it's included the exhibition areas in the top as well as the bottom. Now we're going to do one more thing here. Just hide all of this. Now what we want to do is color each of these areas according to the program. So all of the exhibition areas are going to be one color. All of the terrace areas are going to be another color, and so on. The way that we can do this is by taking the total number of items in the program set and create a series of numbers based on that. But just so you can sort of understand what we're going to do, is we're going to create a range of hues. Hues that define a color go from 0 to 1. So we want to create a range of values from that more or less span the difference from 0 to 1 and correspond to the total number of values in the set. So what we can do is divide 1 . Maybe so you can see here. Divide 1 by this number and create a series of numbers. The series length is going to be this, and the step size is going to be this. And so that creates, if we've got a set of 4 programs, then we can create a set of 4 numbers, and which are going to be turned into a hue. Now we can just rebuild this according to that data structure and multiply the color values according to the length of the list in each program branch. So you read off that length, and so you've got matching values here and here. And that should have matching values here as well, over here. So we can display everything according to those colors. Okay, so there's a few things that aren't working here. So for example, none of the first floor is showing up. And actually, why is this? Oh, so you can see the text was actually placed a bit off from the plane where it was supposed to, because I just copy pasted it in a really messy way. So first, if we take the text in the first floor and place it exactly at the first floor level, okay. So now the surfaces are being detected. However, there's still a problem here at the bottom, where the foyer is the same color as the terrace, which means our layer structure must be a little bit off. Let's just hide that. Actually, this is why. I actually need to connect it to the plane that's been shifted, because here we've got them in a branch system that's slightly different to this input, and it's similar to this one. So this is where we have to put them in. And so that seems to be working out properly. So we've got exhibition, same color, foyer, cafeteria, and the terraces are purple. So now this is working properly, and everything is adding up correctly. And if I wanted to just work on the first floor, then I unclick here. And now this is showing me just the first floor, or just level 0. And so if we go back to here and we hide all of the text from first floor, I can add, say, a new element called toilets, and you can see how this is working. It's just recalculating all of the color system on the fly, and I can remove this one, and then that's perfect. Everything is being maintained. And so if I keep this window open while I'm sketching, then I can keep track of exactly how much each program is taking up. See? And I can reduce it, and I can check my totals as I'm working. And if I want to get really fancy, I might just add all this up, flatten it, and divide all of these by this total number. Multiply that by 100. And there it is, the percentages. So I can also keep track of not only total area for each program, but also what percentage that is of the total. So next lesson, we're going to put this into a spreadsheet. Hi again. So this is going to be a quick video to show you how to first export the program table as an Excel file, and then also to show you how we can then bake these surfaces with color information into Rhino geometry so they can then be rendered out as a diagram or exported to Illustrator or something. So first off, we're going to need the Excel read-write component, which can be downloaded from Food for Rhino. And then that will have the Excel write function in it. And all that this asks for is a path, which is what the file should be called. And I already wrote that down here. A true or false Boolean switch so that it knows when to write the file. At the moment, it's going to be false. And the sheet information, which is a data tree. So now that just means that each column should be its own branch. And the way that we do that is simply to merge each of these lists and flatten them. So you get a list with all of the contents of the first table, then all of the contents of the second one, then all the contents of the third one. And then what we want to do is, no, that's not the one. take the length of these lists and just flatten this before you take the length so it knows it's 5 items. And then use the partition list component. So divide this list into branches with 5 elements each. And that gives you your data tree. 3 branches with 5 elements in each. You put that into here. Now what you can notice is that if you look carefully here, it has some of these elements have 0 square meters and 0% of the total. That's because remember that we included a switch here to control whether it's just displaying the level that you've selected or it's displaying everything. So if I change this, it's going to display the first level, which has exhibition in it and as a terrace as well. So everything will be 0 except exhibition and terrace. Now, I can export this table per floor, or I can just switch on this toggle that we created, and that will have all of the areas in the entire building that have been labeled. And so that has the totals. So now we can just click true. And that will have made a table. So that's got a table with all the information in it. And anytime you want to update this, you just click on this again. So that's how you export an Excel. Now, what about the colored surfaces for use in Rhino? Now that's going to be done from here. Now, using the same human plugin that we use to import text, in this menu, it also has a bake geometry component. And the cool thing is that you can add attributes to the geometry that you bake, not just the layer. Whereas the normal Grasshopper bake only bakes it into a layer that you specify, you can specify many more things here. Among them, a color or a material. So, if we simply take the color information, which came from here for our display geometry component, input it here, then that's the only attribute that we want, unless you want to specify each layer individually, but we don't necessarily want to do that. And then the geometry goes here, and then it just wants a Boolean switch. So whenever you click true, it's going to bake it. And because we haven't specified a layer, it's going to bake it to default, but that's okay. You could just specify anything that you want. So there it is. I can close Grasshopper. And all of this program diagram has been exported to the correct layer. Hi again. So at the moment, we've got a script that allows us to sketch and in real time shows us the areas for the individual areas that we're sketching. When we write a text description of the program, it assigns that program definition to whatever space it's in. Then it assigns it a color based on each unique program and also tallies up the areas according to that program without any need to modify the script. So the last thing that we're going to do to it to make it a really, really useful sketching tool is to have it draw walls around the areas that are divided by wall lines. So that's why we had a separate a differentiation between division lines and wall lines. We can sketch anything that we want with division lines or wall lines, and the areas will all be computed, but only the things that are drawn using wall lines will have walls drawn on them. So to start, we're going to need to make this a little bit redundant, because the information that's going into this splitting part, where it splits a surface into individual areas, it's a combination of wall lines and division lines. So we're going to have to recreate this part using only the wall lines. So that's going to mean duplicating a huge chunk of this script. It's going to be all of this minus this, which is just displaying areas. All that we're interested in is the geometry parts. So we'll duplicate all of this and move it underneath here. And instead of having both of these inputs to the script, we're just going to have wall lines. And so what comes out of here is a set of surfaces. So that's what we're going to start working with. First thing we're going to do is graft each of these surfaces onto its own branch, because now we want to extract all of the curves, because we're going to make all of the walls out of these curves. So the way we do this is explode these surfaces and then join up the individual edge curves. Now we're going to want to establish the width of the curves. And also, the way that we're going to do this is we're going to have all of the interior partitions are going to be one width, and all of the external perimeter walls are going to be another specified width. That just gives us a bit more control over this. So let's say that we want the interior walls to be 30 centimeters. So since we're drawing in meters, just write 0.3. And we'll divide that by 2. And you'll see why a bit later. It's because what we're going to do is offset the curves. So what you want to do is actually some of these have more than one curve in them because these surfaces have more than one a closed edge loop. So we just have to graph that. The distance, we're going to use this. So we're going to be using these lines as a center line. So it goes inside, and we also want it to go to the outside as well. Because the thing with offset is that you're never really sure which way it's going to offset. So some of them will be offsetting toward the outside, some of them will be offsetting toward the inside. So we're going to do both and then select the interior one. The way that we do both is just use the negative of this value and also introduce that as a distance. And so you can see that now both sides of each of these are being offset. Now what I'm going to do is all of the curves that have been offset, which are touching the actual surface, are going to be kept, and the ones that aren't touching it are going to be removed. So it just needs to compare each curve to each surface. So now what we want to do is shift the range. So that's going to put two offset curves on each level, on each branch, sorry. And we're going to test just one point of each of these curves to see if it lies on the surface. So we'll just take the start point of each of these curves, and we're going to see how close it is to its surface. Now all we have to do is it's because some surfaces have more than one edge curve, as we saw. What we want to do so that the data trees match is duplicate the surfaces by the number of resulting edge curves. And that should give us a data tree that matches, with one for each set of offset curves. And basically, whichever one lies closest, we'll just sort them according to this. Sort the curves are here. And the first one is going to be the one that lies the closest. So we just extract that one, and we should have all of the curves on the interior. So the smaller offset, the interior offset. Now all we need to do is do the same operation, but for the perimeter curves. And what we're going to do is take each of these. We're going to have to do something a bit extreme, but it's going to work out in the end. We're going to flatten this, and we're going to join up all of these surfaces. The ones that can be joined up will be joined up. And that's why we have to flatten it so that they're all operating on the same branch. And then just to make this a bit neater, we're going to merge the resulting faces. to get one clean, uninterrupted surface. And we're going to graft this, and we're just going to take this entire bit and copy it over. Except we're going to change one thing. And that's how wide we want the walls to be in the perimeter. So maybe in the perimeter, we want them to be 0.8. Or maybe 0.5. However, this is now still calculating the interior curve. So the only thing that we have to do to make it find the exterior offset is just reverse this list. And that's about it. So what I want to do is just hide all of this. And maybe also hide the results of the program coloring. And now we're pretty much ready to make surfaces out of all of these. So preview on. And you can see that's already drawn the polylines. And this is pretty much ready to export. And what you can also see is that all of the lines in green are not taken into account because they're the ones on the division lines. The ones that are drawn in blue are the only ones that are taken into account. So let's just try to make surfaces out of these. First, you're going to want to flatten all of this. And then it should be neat enough that you can just tell it to go wild, make surfaces out of everything that it can, and it will be making the proper hatches. Now, I have this set to do all of the floors, but for example, if I'm drawing only the ground floor plan, maybe I'll just do this here. And I don't want all of this visible. First, I'll just hide all of the layers. And then remember that we had a switch that controls whether we're calculating all the floors or just one of them. So we just unclick this, and then we can do it by level. We can see all of the levels here while we're sketching. So say, for example, in level 0, I want to remove this. I just change that to a division line. Everything remains the same. The areas remain correct. And it's simply just drawing walls around where there's a wall line. And so once again, if I want to draw an interior circle here with a wall line, it'll draw the walls and it'll also calculate the areas. If I then change this to a division line, no wall, but still the areas are calculated. This is really useful because you don't want to draw walls everywhere. And you might want to have just a circular area for seating or so on. And you want to be able to calculate that into the program, and you don't want it to be partitioned off. So that just adds that extra bit of flexibility to the tool. And so all of this is quite easy to export. You can export the individual curves by baking this, or you can export the surfaces by baking this, and then you can either hatch this or then possibly export these curves and then extrude them. Or what we could even do is turn this on and have all of them be calculated. And since all of my floors here are the same height, I could just work with these surfaces to make an extrusion. And so that starts to build a model automatically. And of course, this is nowhere near the detail level of a proper CAD plan, but it's a really good start to making a quick sketch. Then you can start to work on wall widths and so on, adding detail. But once the sketch is solid, once the areas check out, once you know you're meeting the program, then it all becomes much easier. So CAD becomes an exercise of adding detail and not playing around and making it work. So the playing around bit you can do very, very quickly with the sketch tool, and then work detail into CAD. Hi, so last video we created a layer structure that will allow us to sketch very simple rough lines, have Grasshopper read them, and return information to us about them. And so what I did was sketch out a very basic set of shapes on the ground floor layer. So at the moment, this is all happening at level 0. Now what we're going to do in this video is make it so that the wall lines and the division lines are read by Grasshopper. It creates surfaces for each of them, calculates the area, then displays the area in real time on the sketch, which means that while we're sketching, we see the exact areas of all the polygons that we're sketching. So let's just open Grasshopper. And we're going to start by creating a geometry pipeline for 3 different layers: the wall lines, the division lines, and the voids. So you have to type in the exact layer name here and it'll read it, and then type in the type of geometry. So it'll just be curves. And then it will have read all of the information in that layer. So this will be division lines, and this will be voids, void. And this won't be curves, this is going to be points, and we're going to see how that works a bit later. So that's the information that we're working with. Next, whatever comes out of here, I'm going to want to split it. Now both the wall lines and the division lines for this part of the exercise are going to go into the same operation. So the areas are going to be calculated whether you draw division lines or wall lines. Later, we're going to want to make a differentiation because wall lines are going to be used to draw walls, whereas division lines are not. But in this case, they're just going to go to the exact same place, and we haven't drawn any division lines, so there's nothing there. And this can be flattened. So that's all of the curves in every layer, called wall lines and division lines. You can actually see them highlighted here. So what are we going to do with them? We're going to use all of these to split a large surface that's much larger than the bounds of this drawing. So in order to do that, it's just easy to take any point that lies on here, just take the start points, and then just take any start point that you want, just as long as it's just one, because we only want one surface, and then use that to create plane, which we're then going to use to create a large four-sided polygon. Number of segments, we want 4. And then for the radius, we actually want to enter something really, really large. So if we just write 1000, because I'm drawing in meters, and I want to try to keep all of my parameters here, just because you don't want to be traveling within the definition to find all of the sliders and inputs that you need. So I try to, everything that you need to establish, I try to move it to the left. So just have that as a radius. And then if we zoom out here, it's created a really, really big surface, much bigger than anything else. And that's what you want. If you're drawing in millimeters, well, you're just going to have to add a couple of zeros there. Just make sure it's much bigger than your drawing, and then your drawing's within it. So, okay, that is going to be used to make a surface. And that surface is going to be split by all of the curves. Oops. So now it's made a series of surfaces. Now, the only thing we want to do now, in order to move forward from this step, is just take the largest surface, which would be all of this leftover space, which is a single surface, and remove it. So let's just measure the area for each of these, then sort the list of areas from smallest to largest, and consecutively sort each surface. Then you want to reverse that so that the largest surface would be first, and just eliminate surface with index 0. And there they are. So just hide everything else. And we've got our surfaces here. Just group this. And call that split surfaces. So these are the surfaces that we're going to be working with. And you'll notice that I can move anything here, and the surfaces are getting recalculated, retrimmed as I draw. Now, we may not want all of these surfaces to enter into our calculation. Some of them may be voids. So what we want to do now is for each surface that is touching a point placed in the voids layer here, I want to remove that surface. So let's just add a point on the voids layer. There it is. Now that's going to be read in here. Now I've got a single point here. But actually, what happens if I don't have any points? Remember that since this is a tool that we don't really want to be modifying this script, and we want this tool to work in all cases, we have to add a point there always has to be one point, otherwise the script is going to freak out. And an easy way to do that is to add a point from our very large polygon here. Just get a start point here. And make sure we add that to whatever we're doing here. Just merge it. One of these, this one point in here. You might want to flatten this. Okay, so everything that's touching, every surface that has a distance to any void point of 0 is going to be removed. So we simply have to take each of these surfaces, and we're going to want to graft this here. And the component that measures the distance of a point to a brep is here. So take the surfaces here and input the points here. Now every single point that's in a layer called void, its distance is being measured to each of these surfaces. So there's 2 points, and you can see in the file structure that each surface is being measured from 2 points. So we just might sort these according to distance. Choose the smallest distance and ask whether this is 0. However, sometimes Grasshopper is really weird about whether something is 0 or really, really close to 0. And sometimes it doesn't detect that it's 0 even if it is. So what we're going to do is ask it, is it greater than a very small number? So I'm drawing in meters, so I'm going to use a number like 0.01. So that would be the tolerance. And so we can just use that as a way of removing every surface. We'll just take them from here. Every surface that is touching a void point gets removed. Let's just hide this. Actually, let's hide all of this. Preview off. And there it is. As soon as I draw a void point here, it removes the surface. I move it, and that surface gets removed. I can copy it. And all of these are getting removed. So the goal here is making a tool that works for speed so that you can just minimize this and just add points as you see fit. Sorry. And be able to draw and get information back really quickly. So we're going to call this part eliminate voids. Now, after we've got the set of surfaces that we want to analyze, we're just going to add an extra step where we take each of these surfaces and first, if we removed something, there's an empty branch. You can see it there, that's 0. There's a branch with nothing in it. So we want to clean that up. And using clean tree, this component is able to remove empty branches. So you just, there's remove empty branch option and set boolean true. And there it is. It's removed all of the empty branches. And now these surfaces, we want to explode them and take all of the edge curves and join them. And also try to use simplify curve. That's just going to allow us to remove any errors that were made through splitting, because splitting surfaces can get quite messy. And so, for example, you can see that one of these polygons actually has 17 sides. That doesn't really make any sense, does it? So we simplified it, and now it's got 4 sides. And now just using this, we'll make new surfaces from this. Again, it's useful if we just hide the steps that we've been going through. Just testing for errors. So group that. Let's call it rebuild. Now, finally, what we want to do is we can already read the areas for each of these surfaces, but because we want to display them in the most convenient way possible so that it's really useful when we're drawing, we want to know where to display all of this information. And you can see that this component, this gives us the area and the center point. But if we display the area as a number at each of these points, then we have a problem where, say, I've got this area and it's intersecting with this area, and suddenly I'm going to get 2 areas being displayed here. And those little mistakes add up and make this tool really messy. So what we're going to do is we're going to find a new way of calculating the center point. And it's actually not that difficult. It's not as simple as this, but it's not difficult. What we want to do is for each of these surfaces, calculate a list of points on it. 10 by 10, it shouldn't make it too slow. You want to have a good range of points, and it's going to select the point that's farthest away from any curve. So actually, this component does something that's not really useful for us right now. It makes rows and columns into branches. So you've got, 11 branches with 11 points on it when you want just 100 points in one branch. So actually, first all we have to do is shift the paths. And now we've got 121 points corresponding to each of these surfaces. So that's great. And there's a component that will measure the distance of each of these points to each curve. Now the curves are here, not the surface. So there we are. And now this distance, we can just use it to find, again, by sorting, the point that's furthest away from the curve. So here we go. Here is the list of distances that's been sorted, and we want to sort the list of points synchronously. And because it goes from smallest to largest and we want the largest, we just reverse this list of points that have been sorted. Take the first one, and if I hide this, the problem that we used to have, see, the points get reconfigured every time you're moving. So this point that was here moves over here. And that's exactly what we want. It's always shifting out. And so that's going to be the way that we're going to calculate. Oh, let's just group this. Keep it neat. We call it find center points. Now the center points are going to be used to create planes. Planes are going to be used to display text. It's over here, 3D tag. So the location, you want that to read the planes. The text, we want the text to be the area. So we do want to read the area off each of these. But because it's an area, we also want to turn it into an integer. So let's just do this. And since we're drawing in meters, a size, the default size of 1 is perfect. So there it is. It's displaying the size of each of these. And if I remove this void, it's displaying that area. Now the cool thing about this is that I can just minimize this and start sketching to my heart's content. And start sketching more wall lines any way that I want, and it's splitting everything up. Everything that I alter here is going to alter the result. Now, you can get pretty creative with what you can do. See, all of these have their own areas and all of them are being calculated in real time. So you can move any point, doesn't matter the geometry. And you can get quite Libeskind here if you want. And everything is getting updated in real time, so you have a real sense of what type of spaces you're creating. And this is a real lifesaver in, say, maybe a competition where every, bathroom is specified to an exact area, and this is perfect. And this not only works with, polygons. I could sketch with any type of curve that I want here. and it's working everything out in real time. So again, the goal here is to create a tool that gives you feedback in such a way that it becomes much faster than drawing in, say, AutoCAD or Revit, where, yes, you can get all this information, but you're not tailoring the tool to your needs at the moment. This is a tool for conceptual sketching in a really, really quick, intuitive way. So this is the first part of what we've done. We've just created a real-time readout of all the areas in our sketch.